Hello everybody, I hope you're doing well and welcome to the platform of CodeChef. So today we're going to be solving the problem Charlie and prime numbers. The difficulty level for this problem is simple and the prerequisites require are your C over Astronesis. So this is your educator Ansh and I hope you like my video. Let's proceed to the problem statement. Now let us try to understand the problem statement. Basically, Charlie has a fascination for prime numbers, but he never went to school so he always makes a mistake when he asks to tell whether a number is prime number or not. So he asks his brother Alan to help him out. So your job is to help Alan in writing a program which prints the sum of all prime numbers between m and n inclusive. So basically in this problem, we are given two integers m and n and we have to print the sum of all the prime numbers lying between it. So as you can see in my sample test cases I have my 1 and 8. So all the prime numbers lying between 1 and 8 are nothing but 2, 3, 5 and 7. And sum of these numbers is nothing but 2 plus 3 plus 5 plus 7 which is 17. Similarly for my other test case my m and n is nothing but 37 and 45. And as you can see the prime numbers lying between 37 and 45 are 37, 41 and 43. And the sum of these prime numbers is nothing but my 121. So this is what the question is trying to say. Now let's see how we can approach such a problem. Okay, now let us try to understand how we can approach this particular problem. So firstly, in order to generate all the prime numbers, we can simply use the algorithm for C of Eratosthenes. So I've written here the pseudocode for C of Eratosthenes that simply we can traverse from 2 to square root of n, and then if my prime array of that particular number of I or just I is true, then I can traverse my j loop from I plus I to n with an increment of I and set my prime value of j is equals to false. So what I mean by that is firstly we'll traverse from 2 to the square root of n. So square root of 17 is around 4, right? And we can just, to be safer side, we'll traverse from square root of n plus 1, which is 5, right? So let's traverse till 5, and then what we can do is simply we can mark every multiple of each element to be false. So what I mean by that is firstly I'm on 2. So for 2, I'll mark every multiple as false because that cannot be a prime number since it is a multiple of 2 and a prime number has only divisors 1 and itself. So if my 2 is divisor, it obviously cannot be a prime number. So basically I'm gonna mark 4 as false, 6 as false, or all the multiples of 2 as false. So here I'm marking my all the multiple of 2 as false. Then I go to my next number which is 3. Then I mark all the multiple of 3 as false. So already number which are false are fine. And so I mark 9 as false, 12 is already false, and I mark 15 as false. And then I go to 4, or 4 is already false, so we can just pass because if my prime of array is true, so basically initially all my elements in this configuration were true. But as we keep on marking them, they become false. So my 4 is false, so I can just avoid. And then for my final configuration, which is 5, I can just mark all the multiples of 5 to be false. So 5 itself is, so my 10 is false, my 15 is false, and yes, that's it. So as you can see, I have finished traversing square root of n and rest all my elements are true. So true, true, because by default they were true, right? So as you can see, my all the remaining elements are nothing but your prime numbers. So 2, 3, 5, 7, and my 11, and my 13, and my 17. So all these numbers are my prime numbers. So this is how we can generate our prime numbers in simply time complexity of big O of n log n because Ceef has this particular time complexity. So what we'll do is, firstly, we can generate our prime numbers for the max n, and as you know in this question, the maximum value of n in this problem can be 10 power 6. So we can just generate all the prime numbers up till 10 power 6. Then what we can do is we can keep a prefix array. So what do I mean by that? Once I'm done with getting my prime numbers, I can just take that prefix of I for any particular index will be nothing but sum of all prime numbers up till that particular index, sum of all prime numbers up till that index. So basically in this case my prefix of firstly 1 will be 0 because there are no prime numbers till 1. Then my prefix of 2 will be 2 because there are one prime number that is 2. My prefix of 3 will be 5 because 2 plus 3 and there are 5. My prefix of 4 will also be 5 because up till 4 there are two prime numbers whose sum is 5. My prefix of 5 will be similarly 5 plus 5, which is 10, and so on. We can generate our prefix array, right? So basically, if I want to find how many prime numbers are there or what is the prime number sum lying between my 2 to 5, I can easily get the answer between prefix of 5 minus prefix of 2 minus 1, because we have to take 2 inclusive, right? So basically, we can just subtract this particular prefix with prefix of 2 minus 1 in order to get this range. So then my answer will be nothing but 10 minus 0. So as you can see, our sum is nothing but 2 plus 3, which is 5, and 5 plus 5, which is 10. So for any general R and L, I can simply get my answer as prefix of R minus my prefix of L minus 1 after generating the primary. So the approach for this problem becomes simple as that you generate all the prime numbers using the sieve, and then you compute the prefix array, and then for any particular test case when you're given m and n, the answer will be nothing but prefix of r minus prefix of l minus 1, which is a greater number. So this becomes the approach for solving, and let's see how we can code this particular problem. Okay, now let's try to understand the code for this following problem. So here I defined all my particular constants and all the header files. Then my find primes will implement for nothing but find prime numbers. So what it does is basically I initialize my prime of 0 and 1 as false, as my 0 and 1 are not a prime numbers. And then for simply 2, I initialize all my primes, initially all the elements are currently true. Then I apply the sieve algorithm as I discussed in the approach section, and I initialize all the multiples of the numbers of prime, or whichever prime numbers are present, we just initialize their multiples as false, and because they're obviously not prime numbers. Then simply after we calculate or we generate our prefix array as I discussed in the approach section, right? So after generating a prefix array, for main function we can just simply call the find prime function so that our entire array will be initialized, and then for each t-test case we can simply input m and n, and our answer is nothing but prefix of n minus prefix of m minus 1 as I discussed in the approach section. So let us run our code in the sample test cases to see whether everything is working correctly or not. So as you can see, we got the expected output correct for the following test cases. Now let us submit our code on the actual test cases to see and understand whether everything is working correctly. So as you can see, we got the correct answer for the following problem, and yes, this becomes a valid approach for solving this problem. Now let us see what people can do wrong in this particular problem. So here I have a sample code which got a time limit exceeded error. The error was gotten because the person did not apply C of Eratosthenes. He used a simple or traditional prime approach to find the prime numbers. The time complexity of this algorithm is nothing but n square root n, and in the given constraints I'll get a time limit exceeded error for that particular time complexity. So C has a smaller complexity of n log n, and that is enough to pass this particular solution, and hence one should implement in such a pattern and not in such a way. This is the learning you get from this video. I hope you like this video. Please like, share and subscribe to our channel. Thank you.